丘成桐先生担任中评审委员会主席，秉持科学公正的原则，严格遵照评审流程和标准。这是国际基础科学界的重要奖项，为青年迈上研究之路指引方向，为人类探索未知世界照亮航程。
We chose over 100 people who have done their best work in the last 5 years, and they come and they will be presented with some awards for the recognition of their work.
I want to greet the International Congress of Basic Sciences, which will be held in Beijing this July, combining both all mathematicians, physicists, and computer sciences. I wish a great success to this event.
I think it is a very important event for scientific community this year. I myself also looking forward to meet many top researchers.
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together to exchange cutting-edge ideas. I'm looking forward to attend all these exciting talks.
We are very happy to see the best minds come together to discuss the four.
尊敬的各位来宾，本次会议将于5分钟之后开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly in 5 minutes. Can we please ask for you to kindly take your seats? We would also like to remind you to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
无穷的宇宙，基础科学不断拓宽人类认知的边界与疆域。这是基础科学的盛大聚会，这是一场顶尖的智慧交锋。让我们以基础科学之光，点亮人类的未来。
数学是很有意义的一个学问，我们解决一个好像表面上一个简单的问题，但是可能影响了很多其他的学问上。
应用数学是要从应用以及技术角度看，以应用场景为导向的数学研究。
我们是从事应用研究，就是要解决实际问题，
而这个实际问题一定来自社会经济发展的重大需求。
陈市长大概3年前邀请我到他的办公厅里边交流，他期望我办一个以基础数学来发展应用数学的一个研究院，期望这个研究院能够带动中国的基础科学的发展。
我们有75%的应用数学，25%的基础数学，其中想的是把基础数学和应用数学真正的结合起来，然后起到一些引领的作用。
所以我们一开始就重视了怎么引进人才。
我是2019年从新加坡国立大学回国的。
尊敬的各位来宾，本次会议将于1分钟之后开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly in 1 minute. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
因为我们的年轻人这个水平很高，也因此能够吸引到世界上有名的大师。
When I was younger, math brought me joy because I was just naturally good at it. But when you study enough math, you learn that math is really hard. And so maybe some of the joy disappears and is replaced by curiosity, it's replaced by a sense of challenge.
ladies and gentlemen, let's start the conference. This is one of the most exciting conferences I've ever had in my 50 years of working in mathematics. We see the best mind that I have ever been able to gather together in this center. So each of them are great men that I admire. So we actually, in BIMSA, we have a very beautiful campus, as you will see soon. You will see the Great Wall behind us, and I hope you admire it. And you probably can also drive to there to take a look, about half an hour. And we are, behind us is the Great Mountain of China, which is supposed to protect Beijing city. Historically, whenever the Mongols invade China, if they can bypass the Yanshan Mountains, Beijing is gone. So this is one of the most important defensive spot for the city and therefore for the whole China. We were told by Beijing City to build this center about 4 years ago, and we moved rapidly. We have more than 150 researchers now, one of the best centers in the world, and we are trying to get even better. We can double the size of the center, both physically and manpower. We have the funding to do it, so I encourage you to take a look at our campus. In the meanwhile, we form a small exhibit. We try to build a museum of mathematicians on campus in the future. But right now, we form a small one. Some of your pictures are there. So I recommend you to take a look. This center is across our hall within walking distance. We will give you the poster. Most of your pictures are there. Those who got an award, we will try to exhibit in that center. So today at 2 p.m., we have a small opening for that center. In case you are free, please come to take a look of the center. We have a genealogy of all mathematicians and all that. So I think it's interesting. So now come back to our important event now. Well, I knew Andrew Wise for a long time, not well, but on the other hand, I always admire his accomplishment, especially by the time when he finished the famous Taniyama Wave Shimura conjecture. So that was a spectacular work. I should just say a few words related to that. I remember when I was young, when I was a graduate student in 1970s, my teacher, Chen, told me the greatest mathematician in 20th century, he mentioned Hermann Weyl and Andrei. Both of them has helped Chen for his career. So he said these are two greatest mathematicians in the century. And then after Andrew solved the Taniyama Wave Shimura conjecture, I was told, Wei said that now one should not confuse my name with Andrew Wise. There are now one more W. There will 3 W who are the greatest mathematicians in the 20th century. So we are very grateful and happy to have Andrew to be willing to receive the award that we gave and also give this grand lecture, the Langley project. So, Andrew.
Thank you, Professor Yao, for those kind words and for this invitation and this award. It's a great pleasure and a great honor to be here in Beijing. So number theorists have been solving equations for hundreds, perhaps thousands of years. And the one that captivated me as a child and afterwards. First was the Fermat equation, which of course, as almost everyone knows, is the equation x to the n plus y to the n equals z to the n. And you have to show there are no integers. Inspire mathematical research, and they are also in many ways a measure of our progress in number theory. Much of the work in algebraic number theory in the 19th century was inspired by this equation. And this equation has inspired again in the late 20th century revolutions in the study of the Langlands program. Now that it's solved, the next problem, which number theorists are perhaps most obsessed by, the next equation rather, the problem of elliptic curves. So equations y squared is x cubed plus ax plus b, where a and b lie in a number field that is some finite extension f contained in the complex numbers. But to solve these equations, which are essentially in two variables, the first in affine form would be in two variables, we first have to understand equations in one variable. So an equation in one variable, and the solution, of course, is a p-th root of unity. What studied Fermat's equation using these numbers and made great progress, abelian extensions of the rational numbers. So the Galois group of q's a to n over q, and one can describe it explicitly as here. You take a to the element sigma a, abelian extensions. But a very profound theorem of Kronecker and Weber, the abelian extension of the rational numbers is a subfield of the cyclotomic field. So even from the beginning, the question of what should replace this in the non-abelian case was present. But first, I want to, roughly 1890 to 1930 and beyond, was, well, these are the abelian extensions of the rational number. So the first, particularly what class field theory is about. It's a bit solving y squared is x cubed plus ax plus b in a quadratic field and over the rationals. Then you find there exists an abelian extension m of f such that the Galois group of m over f is given by z root 5, the ring, modulo the ideal p generated by p and 1 plus root 5, and take the units in that quotient. This m replaces the p cyclotomic field over q. If you take a similar construction over the rationals, you would get back the cyclotomic fields, or the real subs. And others hoped that you'd have something analytic that would generate it, like the roots of unity are values of the exponential function. But this m is not just an existence theorem, but it's actually one can characterize it, and that's what class field theory does. So you characterize it either by the splitting of primes or by the norms from m to f. You can describe it in some rather complicated but very natural way. But the fundamental fact, which was found by Artin in 1922, is that there's a canonical isomorphism. I'm not going to describe that at this point, but I will give examples subsequently. And it's very profound, and I hope, let me just say a word about proofs. I'm not going to talk about proofs. The proofs of class field theory are very complicated, but the idea, which I tried to crystallize, something like the following. Suppose that M is an abelian extension of F of exponent n. That means the Galois group is a quotient of products of cyclic groups of order n. Then if we attach the nth root of unity to F, so we start with F adjoin an nth root of unity, F zeta n, then we can find all the abelian extensions by extracting roots, nth root of alpha 1, nth root of alpha 2, and so on, where the alpha I are in the field F zeta n. So Kummer tells us how to do that. We know the abelian extensions with this zeta n adjoined. And the crux of class field theory is to calculate which ones descend to F. It sounds like it shouldn't be such a hard problem, but it turns out that it is. And the basic arguments, originally at least, were separated into two kinds. Counting arguments, which nowadays are thought of in terms of cohomology, but in fact were some of the origins. And secondly, analytic arguments. These involve the L functions associated to such fields and properties at the value s equals 1, using generalizations of Dirichlet's L functions. Okay, well, that's just an idea of the proof, and I'm saying that because I want to make some isomorphism. Because on the left, if it's trivial, that means P is a square mod L, and on the right, by definition of Frobenius, that will be 1 if and only if L is a square mod P. And from Y laws, the role of L and P can be interchanged. Almost every subsequent reciprocity law has lost that. But in this original instance, which is the simplest case of Langler's reciprocity law, the ideas to the case of non-abelian extensions. So first we need some non-abelian extensions. So the easiest way to generate them, the most natural, is from geometry, in fact. So let's take one of our elliptic curves. Y squared is x cubed plus ax plus b. Then using the Weierstrass P function, you can uniformize the complex points of this and describe them, the complex solutions of this, as C modulatis lambda. And from that, it's immediate that the points of order L, the kernel of L to the n on E, or the L to the n division points, are L to the minus n lambda mod lambda, lambda being the lattice. And so as a group, they're just Z mod L to the n Z, two copies of that, Z mod L to the n Z squared. But if the elliptic curve is over the rationals, as I'm assuming here, A and B and Z, then in fact, these points can be acted on by the Galois group, and it gives us a representation of the Galois group of Q bar over Q to GL2 Z mod L to the NZ. In other words, that is our way, one way of constructing non-abelian extensions. And I want to just start with this critical but very basic example. The other ingredient we need for the reciprocity law, roughly speaking, the classical modular forms are as follows. You take the upper half plane, that's the complex numbers with positive imaginary part, and consider the weight 2 modular form, this transformation property, that f of which tells you about non-abelian extensions. In this case, is the modularity theorem, which is also a law, sense of Langlands. And it says that there is this generality. I only explained it for quadratic field. It's as subtle, but anyway, it's some element of the Galois group which you can attach to prime numbers. So the trace of Frobenius should be AP if that's what it is, then there's a modular form which is an eigenfunction for all the Hecker operators, and it's an Langland's reciprocity. See between Galois representations, non-abelian, where you take any f replacing the rationals, and he did more as well. You could replace GLN. The other side on automorphic forms, and they simply didn't exist. So there are a whole set of things that should occur in function theory and analysis that have just never been there. So he made most on specific cases of these predictions, and with some success in some cases. It's helpful to go back to the original setting of class field theory and try and understand how to make this correspond ideas in class field theory and try and see where they should come from. Well, the first is comma theory, and that actually has, a lot of that has been replaced. So it doesn't look quite the same, but it's a notion of potential authors. And let me give you a simple example. Class field theory, the real problem seems to be descent. You've got something like comma theory where you can make the constructions, you can prove reciprocity, but you want to try and descend back to the original setting of the field F0. What are called Hilbert modular forms, so these are generalizations of the original classical modular forms. They're functions on D copies of the upper half plane to the complex numbers, again holomorphic, but this time in several complex variables. They have a weight 2 action defined in much the same way as before, but with respect to subgroups of SL2 of the integers of that totally the eigenvalues of the function of the Hilbert modular form. It's implicit 0 over F0, and F forms of F is contained in F. F is the bigger field. It's a Galois elements of the Quaternion algebra on the left, and by some open compact group on the right. And this group on the right depends. This is given a way of describing trace F0. So I want, for class field theory, so a counting argument which relates the trace on x0 and the trace on x. So cross x, you take the intersection, counted with multiplicity, so this is just a numerical sum. So that the Dirichlet series I write down is a series with positive coefficients. Now, if this were a classical L function, then you can see very quickly that this would tend to have a pole at s equals 1. So the idea is actually because of the way the trace formula relates a geometric side and an analytic side, this is actually, can actually be interpreted in terms of a classical generalization of Dirichlet L series. So in fact, and this implies that you do actually get equality in the counting argument. So the key is this counting argument. Involves some ergodic theory in the style of Linux. But there's a statement that's lacking, and this statement requires some input from outside number theory. Units in the by the second one by some fixed Adel F. Of rationals. 10 years ago, the key ingredient solving these
Well, thank you, Andrei. It's a great talk. I hope we can ask some questions. So, any questions? Yeah.
Oh, thank you so much, Professor Wiles. I'm an undergraduate student at Shandong University, and we all know your legendary story. I really want to ask, do you have any advices for new graduate students?
Let's not ask questions of this type. We are talking more scientifically.
Okay,
please sit down. Please sit down.
Okay, I have a question about this lecture.
I don't want to interview. Sit down, please. Let's ask another questions.
Hi.
Yeah.
Thank you for really beautiful talk. I'm very much inspired by it. And I have a question. You mentioned how solving this understanding reciprocity in a very basic setting. I wonder how this relates to the Birch and Swinnerton-Dyer conjecture. Which one would fall first, or are they?
Theory and do it as analytic number theorists. Theory and do it as analytic number theorists. And they could only do that assuming GRH. So ergodic theory at the moment is still much stronger because Kayutin managed to do it without assuming GRH. I would love to have someone. There are very few people who work. It's hard to know.
So if I understand correctly, you really need the tools, the ergodic theory tools that go into Kayutin's work, as opposed to like just having the final statement of.
Well, at the moment, it's possible the ergodic tools can be replaced. That I could imagine, but the limits of measures results, which he also uses, I've no idea, none at all.
Okay, great.
Thank you.
Thank you.
Other questions? Well, if not, thank you very much indeed, Andrei. At 9:45, when Ed Witten will give a talk. Oh, that was a great talk.
Okay, let's sit down. We shall start at least the classical general relativity. And he keep on developing one by one great breakthroughs in both theoretical physics and mathematics. And he was the major person who applied ideas from theoretical physics to mathematics successfully. Important because of his contributions. And I'm fully impressed by him, the best theoretical invitation to black hole thermodynamics.
Thank you. Thanks very much, Yao, for the kind introduction. And I'm pleased to have the opportunity to give this talk, which will be an introduction to black hole thermodynamics, a topic which, as you'll see, some of you will already be familiar with it, but I imagine to many, perhaps the majority in the audience, it's a completely unfamiliar topic. But as you'll see, it's a topic that has roots that go back roughly half a century. Now, there's one thing that almost everyone knows about a black hole. Entering a black hole is a one-way street. What goes in doesn't come out, at least according to Einstein's classical theory of gravity. The picture I've shown here, I've copied here, is a picture of a computer simulation of what it looks like if you're near a black hole and you're looking at the stars that are behind it. So you immediately notice that there's a hole in the picture where you see nothing. That's because the light from behind the black hole that came too close disappeared into the hole. Another fact you'll see is that there's an obvious distortion of the star field around the hole, and that's because of the way light is bent near the black hole by the gravitational field. So for today, though, what's important is just that what goes in doesn't come out, at least according to Einstein's classical theory. So we could say that for a black hole to capture something is irreversible. Once done, it can't be undone, at least in Einstein's theory. But there's an obvious conflict between such irreversibility and the fact that the laws of nature are believed to be completely symmetric between the past and future, or in other words, invariant under time reversal. More technically, I'm referring to CPT. But anyway, it's believed that the laws of nature have a perfect symmetry between past and future, which contradicts the idea that anything is truly irreversible. Well, before worrying about a black hole, let's notice that the same contradiction arises in everyday life. In everyday life, there are all kinds of things that we consider irreversible. For example, breaking an egg is irreversible. Once the egg is broken, we can't unbreak it. There's even a famous nursery rhyme about this in English. Humpty Dumpty is visualized as an egg sitting up on the wall. And once Humpty Dumpty has a great fall, all the king's horses and all the king's men couldn't put Humpty Dumpty together again. Now, why is it that all the king's horses and all the king's men can't put Humpty Dumpty together again? One reason is they probably don't have the technology to manipulate matter at the atomic scale. You'd have to glue all the atoms together in order to reconstruct the egg from the broken pieces. But even if they have that technology, there's a more fundamental problem. It would take an incredible amount of detailed information about the required states of all the atoms in order to recreate the egg. All the king's books and all the king's libraries would never contain enough information. For example, the number of atoms in the egg is roughly 10 to the 24. Let's compare that to a reasonable size of the king's library. If the king's library has 1 million books of 500 pages each and 2,000 letters per page, then the king up on top of the wall, where Humpty Dumpty was sitting at the beginning. But such solutions are incredibly fine-tuned and are very unlikely to be witnessed in practice. Now, the idea of black hole thermodynamics is that the irreversibility that Einstein's theory gives us in black hole physics is of the same nature as the irreversibility when you break an egg. It's probabilistic and describes what will happen for natural initial conditions that we expect to be relevant in the real world, but not for very special fine-tuned initial conditions that are logically possible. If you drop a table or a chair into a black hole, it's very unlikely that the black hole will spit them out the next day. Just as it's very unlikely that after Humpty Dumpty falls on the ground, he'll spontaneously be recreated and jump back up onto the wall. But it could happen with a positive but prohibitively small probability. That assertion is the spirit of what black hole thermodynamics says. Now, if this is true, it means that Einstein's theory of gravity, general relativity, his greatest creation, is fundamentally incomplete. It describes the average or typical behavior of matter interacting with a black hole, but not the microscopic details. In the analogy between dropping something into a black hole and breaking an egg, which both appear to be irreversible, Einstein's theory is analogous to what physicists know as a thermodynamic description in which breaking the egg is irreversible, as opposed to a full microscopic description by laws of nature that tell you about the behavior at the atomic level and that are invariant under time reversal. In such a microscopic theory, at least in areas of physics that we understand better, nothing is truly irreversible. Apparently irreversible processes are just processes that are prohibitively hard to reverse in practice. Now, you might be scandalized at the claim based on such simple considerations that Einstein's theory is only an approximation. But there's actually another reason that physicists believe that's true, a more technical reason. Einstein's theory is inconsistent with quantum theory, as you discover if you try to use Einstein's theory plus quantum mechanics to compute, for example, quantum corrections to the orbit of the Earth around the Sun. You'll discover if you try to do that the nonlinear mathematics of Riemannian geometry, which Einstein used in developing his theory, doesn't agree well with quantum theory. Now, this somewhat technical reason to believe that Einstein's theory needs to be extended has actually been resolved, at least conceptually, in the development of string theory over the past half-century. I've explained that side of the story in many previous lectures, but today I'm going to focus on the issues that concern irreversibility in black hole physics. There are mainly two reasons for this choice. One reason is that it's an interesting challenge. I've actually never lectured on this subject to an audience as broad as this one, so it's a fun challenge to try to be understandable. The other reason is that although it will be hard to explain this fully, some of the most exciting developments in recent years involve this side of the story. Now, a dream is that the developments spurred by black hole physics and what I'll tell you today, and also the string theory developments that are spurred by more technical problems in quantum gravity, will somehow make contact with each other. Hopefully one day, but I'm afraid that day is in the future. Now, before trying to tell you more about black holes, I should say a little bit more about how physicists since the 19th century understand irreversibility in ordinary physics. The basic concept is entropy. Roughly, entropy measures disorder at the atomic level. Once one specifies the macroscopic state of a system, the entropy is the logarithm of the number of possible atomic states, the possible microscopic states. Well, what do I mean by the macroscopic state? If we're talking about the water and topic specified by saying how many molecules there are and what is their total energy. For a more complex system, there's more information in the macroscopic state. For example, in the case of an egg, you describe the size, shape, and chemical composition of the shell, and similar data about the interior of the egg. But all that macroscopic data would be almost nothing compared to what it would take for a full microscopic description of the state of 10 to the 24 atoms making up the egg. The entropy is then the logarithm of the number of detailed atomic states that are consistent with the observed microstate. So an irreversible process is just one in which the entropy increases. Let's consider the original unbroken egg sitting on top of the wall. It has a huge number n0 of microstates. But the broken egg lying on the ground has a number n1 of microstates that's much bigger still. And the ratio of n1 over n0 is a huge, huge number, much bigger than the number of letters in the King's Library. The statement that breaking the egg is reversible in principle means the following. Take the broken egg sitting on the ground. It has n1 microstates. If you would manipulate, well, of the n1 microstates, there is a tiny fraction n0 that represent initial conditions of a broken egg that will spontaneously reassemble and jump up on the wall. But n0 is much less than n1. If you could put the broken egg in just the right state, one of the n0 states, it will indeed reassemble and jump up. But in practice, it's prohibitively hard to manipulate all the atoms to put the microstate of the black hole, the microstate of the broken egg in one of the n0 states that would have this magical property. I should stress the numbers here are much bigger than any numbers you usually meet in science. For example, in the case of an egg, n1 over n0 might be something like 10 to the 10 to the 23. Let's compare that to other numbers that you might think are huge. The number of atoms in the visible universe is a mere 10 to the 80 or so. And the age of the universe, measured in the tiniest units that we believe are relevant in physics, is only 10 to the 60 or so. So these numbers, which you might think of as giant numbers, are nothing compared to this n1 over n0, which measures the difficulty of manipulating the atoms making up the broken egg so that it would spontaneously reassemble itself. So at any rate, this is what irreversibility means in ordinary physics. An irreversible process is one in which the entropy increases. Differently put, an irreversible process is one in which the number of possible microstates, given the macroscopic observables, increases, making it hard to undo, because to undo it, you'd have to put the system back in one of the special states it started with. The usual mathematical statement about irreversibility is the second law of thermodynamics. It says that entropy, usually denoted as capital S, is always a non-decreasing function of the time t. And this is a statement that's supposed to be true in practice for physically realizable conditions, but not true in theory for every imaginable initial condition. So a corollary, if S is always non-decreasing, is that increases is irreversible, or at least prohibitively hard to reverse. Now, Jacob Bekenstein, inspired by questions from his advisor John Wheeler, asked what the second law means in the presence of a black hole. Remember, it says that entropy always is non-decreasing. But as Wheeler and Bekenstein observed, if you toss a cup of tea into a black hole, the entropy in the cup of tea seems to disappear. Well, Bekenstein wanted to generalize the concept of entropy by assigning an entropy to a black hole in such a way that the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, the entropy should be a property that only increases. What property of a black hole only increases? It's not true that the black hole mass always increases. For example, a rotating black hole can lose mass if its rotation slows down. And that's even believed to be important astrophysically in powering jets that come from centers of galaxies. But there is a quantity that always increases. Stephen Hawking had just proved the area theorem, which says that the area of the horizon of a black hole can only increase. The horizon is the surface of no return. If you cross it, you can't come back, at least according to Einstein's theory. And Hawking had proved that the area can only increase. So the area, I hope you can see it. I'm afraid the whole picture looks black, so it might be hard to see from where you're sitting. But there's a disk here that's completely black, whereas outside of the disk you can see some starlight from behind. But anyway, the horizon is the surface of no return, and Hawking proved that the horizon area can only increase. So it was fairly natural for Bekenstein to propose that the entropy of a black hole is a multiple of the horizon area. For example, according to Einstein's equations, a spherically symmetric black hole of mass m has a horizon radius 2gm, where g is Newton's constant. So its horizon area is 4 pi r squared, which works out to what I've written, 16 pi g squared m squared. However, entropy is a pure number, and area, of course, has dimensions of length squared. So to make a formula that made sense, Bekenstein needed to use fundamental constants to make a unit of area. So his formula, well, as a relativistic physicist, I usually set C to 1, but his formula, but including the factors of Newton's constant G and Planck's constant h bar, this was his formula for the entropy of a black hole, except that he didn't know the constant 1/4 that was provided later by Stephen Hawking. So anyway, Bekenstein proposed that a black hole has this area and then entropy, and then he showed that when you toss the cup of tea into the black hole, the increased area of the black hole because of its gain in mass is such that the total entropy increases. So tossing a cup of tea into a black hole is irreversible according to Einstein's equations, and so we would like to believe then that means that the entropy increases, and if you assign this entropy to a black hole, this Bekenstein-Hawking entropy, then you find that the entropy of the original black hole plus the entropy of the cup of tea is less than the entropy of the final black hole after the black hole has swallowed up the cup of tea. Now, the fact that a factor of Planck's constant appears in the denominator shows that the formula is fundamentally quantum mechanical. If you try to take either Newton's constant G or Planck's constant h bar to 0, this entropy becomes infinite. To make a finite entropy like one expects in real physics, it's very important to have both quantum mechanics and gravity. Now, in part because h bar is so small in everyday terms, Bekenstein's black hole entropy is very large. For example, a spherically symmetric black hole with the mass of the sun has an entropy roughly 10 to the 20 times the entropy of the actual sun. So black hole entropy is much bigger than entropies of familiar things that you meet, if according to this interpretation. Bekenstein's idea was that the entropy of a black hole captures the information lost when the black hole was formed. And he proposed a generalized second law saying that the generalized entropy, which is supposed to be the black hole entropy plus the entropy of ordinary matter and radiation outside the black hole, always increases. So the claim, as I said a moment ago, is that when something falls into the black hole, S out may go down, but if it does, then area over 4g h bar increases by more. Now, famously, Stephen Hawking didn't believe this, but in trying to disprove it, he ended up proving it instead. And I'd like to sketch for you what Hawking discovered. And this was Hawking's greatest discovery. The greatest discovery of Hawking's career was that quantum mechanically, a black hole is not really black. It has a temperature proportional to Planck's constant. As preparation to explain what Hawking did, I want to recall the idea of a Penrose diagram as a convenient way to depict and visualize space-time. So a Penrose diagram is a diagram where you capture important causal relations in space and time with a two-dimensional picture that's visualizable. You assume that space-time is spherically symmetric, and then you plot only two coordinates, the time plotted running vertically. So the vertical direction is time, and the horizontal direction will be space, except I plot space only by imitating the radius, the distance from the origin. So the origin is 0 on the left edge of the picture. That's the origin of spherical coordinates. But Penrose taught us that in drawing this picture, it's convenient to make a conformal mapping. First of all, a conformal mapping that puts infinity at a finite distance. So the edges of this diagram are future infinity. Technically, future light-like infinity here, but I'll just call this curve future infinity, past infinity down here, and spatial infinity is this corner of the picture. But there's one more important thing in drawing this picture. You draw the picture so that radially ingoing or outgoing light rays are at a pi/4 angle to the vertical. So that blue line is meant to be a straight line at a pi/4 angle to the vertical, and it represents the path of a radially outgoing light ray. In Einstein's theory, nothing can travel faster than light, so anything would travel at most at a pi/4 angle from the vertical. You could have a vertical line that just goes in the time direction. That's allowed by causality, but relativistic causality does not allow anything to move at an angle that's more than pi/4 from the vertical in this picture. So what I've drawn here is a Penrose diagram. This was the Penrose diagram from Minkowski space. Now, on the next page, I will show the corresponding Penrose diagram for a spherically symmetric black hole. We'll imagine the history of a star that lived for a while and eventually collapsed to form a black hole. So the orange part of the picture is the part of the picture occupied by the so-called world volume of the star. It looks like the star lived at a point in the far past, but that's an artifact of the conformal mapping that enables us to see the picture. So actually, the star had a positive size in the past. It's just been compressed to a point in drawing the picture. It occupied a certain region in space-time. Eventually, this space-time ends at a singularity, which traditionally is depicted by this wiggly line at the top. Future infinity is again this diagonal line here, and the very, very far future is this point. And the difference of the black hole from Minkowski space is that somebody living at future infinity can't see the whole space-time. Remember, you can only see signals that reach you moving at an angle at most pi/4 from the vertical. So a light ray outgoing could propagate to the observer at infinity on this diagonal line, which is the horizon. But if you're past the horizon at a pi/4 angle, you cannot escape to future infinity, to this black line. Your life will end at this wiggly line up here. So an observer watching the collapse of the star to make a black hole will be making observations at future infinity, which means on this, roughly speaking, on this line up here, ending at this point. And what we're really interested in here is going to be what it will look like long after the black hole formed. And that will be studied by an observer who will be living just near this corner of the diagram. Now, causality tells us that in general, what there is now followed by what there was at an earlier time by solving the laws of nature, whatever they are. So in particular, the measurements that an observer makes up here can be deduced from initial conditions on what is called an initial value surface. And there's a lot of freedom in picking what the initial value surface is, but I've picked this blue curve. The blue curve has the property that its tangent is always at an angle greater than pi/4 from the vertical. So it's what's called a space-like surface. You can think of it as a generalized spatial surface on which you could formulate initial data, and whatever we measure at future infinity will follow from whatever there was on this blue curve. I also picked the blue curve so that it intersected the horizon well outside the world volume of the star, where the quantum fields were essentially in their ground vacuum state, because we're far outside of the star. Now, we're making measurements up at future infinity. Maybe we're collecting light that comes out. And the outgoing light rays will travel at the speed of light, which means at a pi/4 angle from the vertical. So these diagonal purple lines are meant to be parallel lines at a pi/4 angle from the vertical, and they're signals that the future observer observes, which originated from the indicated points here on the initial value surface, the blue surface. Well, the question Hawking asked is, what will you see if you watch a black hole from a big distance well after it formed? That means that you're living up here and you're seeing the signals that come out along those purple lines. Part of Hawking's insight was that although the full details of exactly what you see depend on the precise quantum state of the collapsing star, if you ask what you'll see in the far future after transients die down, there's a universal answer. The key point about the picture is that a signal that's received very late, which means very close to this upper corner of the picture, originated very close to the horizon. you know, if you're past the horizon, you never emerge. If you're just outside the horizon, slightly outside the horizon, you will eventually emerge and be seen by the observer at infinity, but you'll observe at a very late time. So what we see at a very late time, very close to this corner here, originated from the blue curve very close to the horizon. So observations made at late time depends on measurements of the quantum field at short distances. But every state at short distances is equivalent to the vacuum. That's a basic property of quantum field theory. So the late time observations of the observer probe the vacuum state near the horizon at short distances. And that's why Hawking got a universal answer regardless of how the black hole formed. Now we need a very short detour in formulas, which will be more familiar to some than others. I'll try to present the talk so that, okay. There are a couple of slides, and this is one with a little bit more formulas. So here I've drawn again the important part of the picture, the horizon, the far future, the initial value surface, which here, the important part of it is the part just outside the horizon, and here it's drawn in red, and then these parallel bluish-purple lines that are signals reaching the outside observer. Let t be the time at which a signal is detected by an observer at infinity, and let u be any function that vanishes on the horizon. Its derivative is non-zero, and we use it to measure how far from the horizon the signal started. We need to know the relation between u and t, which we get by solving Einstein's equations to determine the propagation of light in the field of a black hole. So as u goes to 0, the time at which the signal emerges gets later and later, and it actually gets later and later logarithmically by this formula. So I won't derive that formula for you. We'll have to accept that that follows by studying Einstein's equations for the behavior of light in the field of a black hole. We can invert that relationship to find that if we make an observation at the time t, it originated at a position u outside the horizon. And you see that if t is large, u is exponentially small. So signals that a late time observer sees originated from exponentially close to the horizon. But what exactly does late time mean? So for example, for a black hole with the mass of the sun, 4GM would be some microseconds, and so, milliseconds, I think. So if t is 1 second, then this exponential is something like exponential of minus a few hundred, which means that u is incredibly, incredibly small, much smaller. With those numbers, u is just incredibly small. So people build elementary particle colliders to probe the vacuum at distances of 10 to the minus 17 centimeters, roughly, is what the LHC reaches. But if you observe a black hole with the mass of the sun 1 second after it formed, you're probing the vacuum at distances much smaller than that. So as I said already, a basic fact in quantum theory is that at short distances, any state looks like the vacuum state. So Hawking got an answer that's universal, independent of how the black hole formed, and just depends upon the properties of the vacuum at short distances. Now, technically, an observer at infinity would be measuring some kind of quantum field. In the real world, you probably would be measuring the electromagnetic field, because the simplest signal coming out of the black hole to observe would be light. And you'd measure light waves coming out of the black hole by measuring the electromagnetic field. Rather than being realistic as that, I'll just say that we're measuring a quantum field psi of t. And what do you measure of a quantum field? Well, you measure correlations between the quantum field at different times. The simplest correlation is a two-point function, it's called, the expectation value of the product of a quantum field at two different times, t and t prime. To explain Hawking's result, we need a slightly longer detour with formulas. So if you aren't quantum field theorists, you may want to disregard the rest of this slide and part of the next one. Near the horizon, a typical quantum field would have a short distance singularity that's power-like. So for example, for a fermion that has spin half in the 1 + 1 dimensional sense, the two-point function has a simple pole. Then we change variables from the coordinate u that's appropriate near the horizon to the time and has the property that it's antiperiodic in imaginary time, that is, it's odd under shifting the time by 8 pi gm times I, where m is the mass of the black hole and g is Newton's constant. H bar has been set to 1. So antiperiodicity in imaginary time in quantum mechanics is the hallmark of a thermal correlation function, in this case at a temperature which is called the Hawking temperature, 1 over 8 pi gm. So this computation is essentially the one by which Hawking discovered that a black hole has a temperature and emits radiation. So I wish I hadn't said h bar to 1, it would appear in the numerator. The Hawking temperature is h bar over 8 pi gm. And that's the Hawking temperature at which a black hole emits radiation. In other words, a black hole, after transients that depend on how it formed, die down, radiates thermally at this temperature. We can now confirm the value of the entropy. So there's a fundamental thermodynamic relation. When I introduced the entropy before, I told you about the second law, that the entropy is non-decreasing, but I skipped the first law, which says that the change in energy in thermal equilibrium is the temperature times the change of the entropy. So using the first law of thermodynamics, for a black hole, we interpret the energy as being the mass, or more precisely, mc squared. We usually set c to 1, but mass is energy by Einstein's theory, so mc squared is the energy of the black hole. The temperature is h bar over 8 pi gm. So from the first law, we can determine what the entropy must be, and we find that the entropy of a spherically symmetric black hole is 4 pi gm squared. But as I told you before, the horizon area was 16 pi g squared m squared. So we arrive at the Bekenstein-Hawking formula that the entropy is the area over 4g. That's in units where h bar and c are 1. So that's how Hawking confirmed Bekenstein's idea and sharpened his proposal. And once we understand that a black hole can be understood as a thermodynamic object with an entropy and a temperature, we can now understand that the irreversibility when you drop a cup of tea into a black hole is quite analogous to the irreversibility when Humpty Dumpty falls off the wall and breaks. And this basic idea has been confirmed by many subsequent calculations over the last half century. Now, because the black hole has a positive temperature and is radiating at this Hawking temperature, if you have a black hole in vacuum, real black holes in the real world are not in vacuum, they're in galaxies surrounded by other stars and things are more complicated. But conceptually, an isolated black hole would spontaneously emit thermal radiation, losing energy and evaporating, according to Hawking. But the timescale is very long. For example, a solar mass black hole takes 10 to the 67 years to evaporate, which you might compare to the age of the universe, that's a mere 10 to the 10 years. So we don't expect to observe black hole evaporation, unfortunately, unless we're very lucky in some way. For example, if very tiny black holes were created in the Big Bang, for which we have no evidence currently. We do observe in cosmology something that's believed to be very similar to Hawking radiation from a black hole, namely the inhomogeneities in the early universe that are believed to have been the seeds for formation of galaxies. Unfortunately, there isn't really time to explain that part of the story today. But regardless, Hawking's calculation is of great conceptual interest. Indeed, it poses a puzzle that's driven a lot of research in the half century since Hawking's work was published. In Hawking's calculation, the radiation that comes out of a black hole appears to be exactly thermal, with no correlation between the different particles that come out of the black hole at different times, except what follows from conservation of energy and from the temperature of the black hole. If that's exactly true, it would mean that black hole evaporation is fundamentally irreversible. It could not be described by fundamental microscopic equations that are invariant under time reversal. To see this, consider a process in which a star collapses to a black hole which then evaporates. If physics is really described by microscopic laws that are fully invariant under reversing the flow of time, the star started in some quantum microstate, and if the equations are truly time reversal invariant, the decay products of the black hole after it evaporates must remember the initial detailed quantum state of the star, because if the equations are time reversal invariant, by reversing the flow of time, you must be able to reconstruct the initial state of the star from the decay products of the black hole. If you had a movie in which a star collapses to a black hole and then evaporates, the black hole then evaporates, you should be able to run the movie backwards. You'd see the decay products come in, form a black hole, which then explodes to make a star. That would be analogous to the broken egg on the floor spontaneously recombining and jumping up on the wall. So it would be a very unlikely process in practice, but if the initial conditions are exactly right, it should happen. And for that to be possible, it must be that the decay products when a black hole evaporates, although they look thermal in Hawking's calculation, actually somehow encode the information of the initial state of the black hole, the initial state of the star. The state of the outgoing particles cannot just be thermal. There must be subtle correlations that contain the information needed to reconstruct the detailed state of the original star. Now, a clue is simply that black hole entropy is so big. For instance, as I remarked, the entropy of a black hole with the mass of the sun is much greater than the entropy of the actual sun, by a factor of 10 to the 20 or so. Many researchers have thought that somehow a black hole having an entropy proportional to its surface area, the area of the horizon, means that the black hole can be described by some sort of degrees of freedom that live at its surface, with 1 bit or qubit for every 4G of area. For example, in a famous article in 1992, John Wheeler illustrated that idea with this picture, where he visualized the black hole horizon being built out of cells of area 4G, and each cell is supposed to contain a bit. I hope you can see that each little cell is labeled by 0 or 1. I'm not certain if it's big enough to be seen, especially from the back of the room. Wheeler talked about bits, but you have to know that the term qubit for a quantum mechanical bit hadn't yet been coined in 1992, so he couldn't have called them qubits. And if you read the article, it's clear that his bits arise from measurements of what we would now call qubits. Now, Wheeler published this article in 1992, but he had been Bekenstein's advisor, and I'm pretty sure he'd been drawing this picture for many, many years before 1992. What I've described up to this point is basically the concepts of black hole thermodynamics from the 1970s. And I've left myself 18 minutes to try to tell you some more contemporary developments. Now, the more recent developments from the 80s all the way to the present involve a somewhat different notion of entropy that's natural quantum mechanically. It even makes sense classically, but I won't have time to explain that. I'll have to be rather schematic because time is short, and also the mathematical concepts involved are more elaborate than what I've been explaining so far. In quantum mechanics, there is an uncertainty principle. A state that has minimum uncertainty, assuming that all possible measurements are considered, is called a pure state. A mixed state is roughly a state that has more uncertainty than is required by the uncertainty principle. So, many of you will know that I'm taking liberties in my characterization of what's a pure state and what's a mixed state. But I believe it'll convey the right idea for those of you who aren't already familiar with the concepts at all, since we don't have time for detailed definitions. The von Neumann entropy measures the difference in uncertainty of the extra uncertainty of a mixed state above the minimum uncertainty required by the uncertainty principle. Roughly, if rho is a mixed state, and it would take n pure states to describe rho, then the von Neumann entropy of rho is log n. So people familiar with von Neumann entropy will know I'm taking liberties again here. The entropy that we've been discussing so far in this lecture is thermodynamic entropy. The relation between them is an inequality. For any quantum system, the von Neumann entropy is no bigger than the thermodynamic entropy. Thermodynamic entropy obeys a second law that I've told you about. In any process that can be realized in practice, it's non-decreasing. By contrast, in quantum mechanical evolution of an isolated system, the von Neumann entropy doesn't change. So for example, suppose I take a cup of water, and which is transparent, and I drip a drop of blue dye into it. And this is an isolated system. The blue color initially is localized, it will spread throughout the glass. As the blue dye is spreading, the thermodynamic entropy will be increasing. That's an irreversible process in practice. Once the blue dye has spread throughout the cup, I can't concentrate it again, except by supplying some, what's called a free energy. Well, I can't make it spontaneously, the dye recollect. But the von Neumann entropy doesn't change. So when the blue dye is spreading throughout the glass of water, the thermodynamic entropy increases, but the von Neumann entropy stays constant. Now, what kind of entropy is the Bekenstein-Hawking entropy? Well, I told you that it increases in irreversible processes. So it's a thermodynamic entropy that obeys a second law. However, it's turned out that the von Neumann entropy is also important in understanding black holes. Well, how does the thermodynamic entropy come in for black holes? An important feature of quantum mechanics is the following. Let A and B be two systems. In general, consider the combined system AB. The combined system AB might be described by a pure state, psi AB, meaning a state with minimum uncertainty and zero von Neumann entropy. Even if that's the case, the individual systems A and B can have a greater than minimal uncertainty with a positive von Neumann entropy. That happens because of a quantum mechanical correlation between the A and B systems. In such a situation, the combined system AB has zero von Neumann entropy, but the individual systems have positive von Neumann entropy and moreover equal von Neumann entropy. In this situation, the von Neumann entropy comes entirely between entanglement or correlation between the two subsystems, and is called entanglement entropy. Now, Raphael Sorkin in 1983 was the first to try to understand black hole entropy from this perspective. Divide space into two regions, A and B. You could make any division, but in the application, B will be the interior of the black hole and A is the exterior of the black hole. The vacuum state of the whole universe is a quantum mechanical pure state, a state of minimal uncertainty. But if we consider the quantum fields only in region A or only in region B, we get a mixed state, rho A or rho B, with a positive von Neumann entropy, which Sorkin tried to calculate. And Sorkin and later his collaborators Bombelli, Cullen, Lee, with Sorkin, found that the von Neumann entropy is proportional to the area A of the boundary between the two regions, but with an infinite coefficient. Now, of course, mathematically, this infinity is a little discouraging. Physicists know that a lot of times, if you ask a question that isn't quite right, you'll run into an infinity, which gets cured with a better version of the question. And what Sorkin proposed is the following. The Bekenstein-Hawking answer was A over 4G. But the Sorkin calculation and the refinement with his co-authors here was done ignoring gravity, which is like taking G to be 0. And infinity times A is the correct answer when G is 0. So the proposal was that Sorkin's calculations were the G equals 0 limit of the Bekenstein-Hawking calculation, and that an improved version of this calculation with G not assumed to be 0 would give the Bekenstein-Hawking answer. Now, 40 years later, a computation just like this has still not been convincingly done. But the idea makes a lot of intuitive sense because it fits well with two ideas. The first is that A over 4G is the irreducible entropy for someone who only has access to the region outside the black hole, outside the horizon. And two, the divergence, the infinity that they found in the entanglement entropy was proportional to the area because it came from short distance, short wavelength modes near the horizon, as if the density of quantum degrees of freedom is 1/4G as in Wheeler's picture. So I think most people in the field believe that qualitatively this is right, even though we don't know how to do the correct calculation when G isn't assumed to vanish. Now, despite the puzzles, it was important to appreciate that in black hole thermodynamics, you should consider microscopic von Neumann entropy as well as thermodynamic entropy. Now, this awareness could make one wonder, although historically this isn't exactly what happened, but you could imagine things developing in the following way. You could ask, is there an area law for the von Neumann entropy as there is for the thermodynamic entropy? So in other words, in the classical limit, the thermodynamic entropy is the area of something, namely the black hole horizon, up to a factor of 1/4G. Well, is there a sense in which von Neumann entropy is the area of something? Well, there is. The first version was found by Ryu and Takenagi, and there were a lot of later refinements by other authors, which I won't have time to tell you about. The simplest setup is to consider a universe with two ends, where here an end, well, first of all, ends is a term used in topology, but it matches the intuitive region. So a universe with two asymptotically flat regions where an observer might live. And let the universe be overall in a state of minimum uncertainty, a pure state. And now let's compute the von Neumann entropy of the part of the universe visible to one observer or the other. Well, the Ryu-Takenagi formula in its simplest form says that the von Neumann entropy of the part of the universe that the A observer or the B observer can see is the area over 4GH bar, where now the area is the area of a minimal surface S that separates the two sides. So for the geometry I've drawn a minimal area surface in the interior, and the area of that minimal area surface over 4GH bar is the von Neumann entropy of the part of the universe that this observer or that observer can see, assuming the whole universe is in a state of minimum uncertainty. Now, I don't have time to explain this properly, but I should say that in general, see, I've drawn a minimal area surface in Euclidean signature, in codimension 1, but in Lorentz signature spacetime, the generalization is that S is an extremal surface of codimension 2 in a Lorentz signature spacetime. Now, in the real world, a black hole forms from a star whose thermodynamic entropy is much less than the thermodynamic entropy of the resulting black hole. So as I told you, the actual sun has a thermodynamic entropy that's 10 to the minus 20 of what it would be if the sun would collapse to a black hole of the same mass. So the star has a tiny thermodynamic entropy compared to the black hole thermodynamic entropy. Now, one thing we know about the von Neumann entropy of the star is that it is only smaller, because any quantum system has a smaller von Neumann entropy than its thermodynamic entropy. When the star collapses to a black hole, see, an isolated star far away from everything else can collapse to a black hole all by itself. That's a spontaneous evolution of an isolated system. In quantum mechanics, the von Neumann entropy doesn't change in spontaneous evolution of an isolated system. So the von Neumann entropy of the black hole when it's born is the same as the von Neumann entropy of the star, and that's no bigger than the thermal entropy of the star and much less than the thermodynamic entropy of the black hole. So a black hole, when it forms in the real world, has a von Neumann entropy that's very tiny compared to its thermodynamic entropy. So in the real world, a black hole is born in a state with a very tiny von Neumann entropy. Then, assuming the black hole is isolated from everything else, it starts to evaporate. When it evaporates, it becomes smaller, and its horizon area becomes less, so its thermodynamic entropy becomes smaller. On the other hand, as the black hole evaporates, it's no longer an isolated system. It's entangled with the radiation it emits, And Hawking's classic calculation from half a century ago shows, or claims to show, that the von Neumann entropy of the black hole increases as it evaporates. So the black hole starts with a big thermodynamic entropy and a small von Neumann entropy. As it evaporates, this one's going down and this one's going up. And after a very long time, according to Hawking's calculation, they meet and pass each other. But that's a contradiction. As first pointed out by Don Page, the fundamental inequality that the von Neumann entropy can't be more than the thermodynamic entropy is violated when the black hole has roughly lived for half of its life, when it's half evaporated. It would violate this inequality if Hawking's calculation is correct. Now, this contradiction actually inspired a recent improvement of Hawking's calculation. With extensions of the Ryu-Takanagi formula for von Neumann entropy, these authors were able to improve the computation of the von Neumann entropy of the evaporating black hole, getting an answer that makes sense even after the page time. So they showed, you see, so the black hole is born with very small von Neumann entropy, very big thermal entropy. At the page time, they meet. When they meet, that means that the black hole is in perfect thermal equilibrium, even microscopically. Although I would need more time to carefully explain exactly what that means. But what these authors showed is that once perfect thermal equilibrium is achieved by the black hole, it continues to be maintained as the black hole continues to evaporate. So saturating the inequality is a statement of complete microscopic thermal equilibrium. In the rest of physics, once that's achieved, it's very hard to lose it. And these authors did an improved calculation I won't explain the details of the calculation that requires refinements of the Ryu-Takanagi formula, but the outcome of the calculation can be described by saying that once microscopic thermodynamic equilibrium is achieved, it's retained at all later times. Surprisingly to most people in the field, it was possible to improve Hawking's calculation in this way without developing any real understanding of the microscopic quantum states of a black hole. So some of the mysteries that have been with us for half a century are still with us. But some of the questions have been answered, and as that happens, one gets more and more confidence in the basic framework saying that the apparent irreversibility in black hole physics is probabilistic, just like the apparent irreversibility when the egg falls off the wall and breaks. Now, I hope I've succeeded today in giving at least an overview of some of the ideas in black hole thermodynamics and some hints about the remaining mysteries. I regret not having a little more time to be more detailed on the second part of the talk, but I hope I've given you at least some hints. Perhaps some of the students here will play a role in unraveling the puzzles. Thank you.
Well, Eva, thank you for the beautiful talk. Let's now have a question. Tom, any questions? Yeah.
Thank you very much for a very inspiring talk. My question, inspired by your talk, is it reasonable to have a kind of symmetry, a duality between the inside of the black hole and the outside of the black hole? The quantum mechanical description that you were describing, von Neumann entropy on the inside.
I'll give a conservative answer. So a conservative answer is that we don't have any indication of a duality between the inside and the outside, but we do have a dual description of the inside holographically. To try to explain it well would really be another lecture, but in certain situations at least, we have a holographic description that's dual to the black hole interior. And that's also, well, that could have been the topic of a different lecture, and it's part of what gives us confidence. It makes enough contact with the things I did talk about today that it's part of what gives us confidence in the story making sense and holding together.
Thank you.
Other questions? Yeah. Raise your hand.
In information theory, people think of entropy as entanglement entropy or von Neumann entropy, but in some microscopic quantum gravity theory, people think of black hole entropy as Boltzmann kind of microscopic state counting. Can you give some comment on these two different concepts of entropy, whether they are fundamentally the same, or one is more general than the other one, or they are just different?
Well, good question. So I didn't explain the inequality I stated, that the von Neumann entropy is no bigger than the thermodynamic entropy. But that comes more or less by investigating your question. So what's called thermodynamic entropy, roughly speaking, thermodynamic entropy is the logarithm of the number of accessible states. And that's also the largest that the von Neumann entropy can be. The von Neumann entropy carries more microscopic information. A cup of water, depending on your assumption, well, a black hole could have a von Neumann entropy as large as its thermodynamic entropy, but in the real world, it's born with a much smaller von Neumann entropy. Okay. I don't feel I'm answering your question very well, so let me take one more try. Von Neumann entropy and thermodynamic entropy agree in thermal equilibrium. But von Neumann entropy is defined universally for any state, not necessarily in equilibrium. For a state that isn't in equilibrium, the von Neumann entropy is less than it could have been, given the macroscopic observations. Well, I hope I've more or less answered your question.
Okay, thank you. Other questions? Yeah. Paul.
I want to see if I understand the idea of von Neumann entropy correctly. Can I say that von Neumann entropy measure a system? How close is it being in pure state?
Yes. Well, it measures that, but it's not the unique measurement of that. I think it's the most important measurement of that, probably.
Let me follow up.
Yes.
Can I express the difference between the thermodynamic entropy and the von Neumann entropy? We know that's according to the inequality, it's a positive number.
Yes.
Can we kind of describe that as some kind of quantum correction?
Well, it's also true classically that you can define an entropy which in general can be less than the thermodynamic entropy. To save time, I only talked about the quantum version. Well, unfortunately, to save time, I didn't write any formulas that would have gone into defining the von Neumann entropy precisely. And that's why, unfortunately, without having any such formulas, anything I say will be a little bit vague. But the von Neumann entropy is defined for any state of a quantum system, and the thermal entropy is what the von Neumann entropy would be if you're in thermal equilibrium, which means if you have the maximum possible von Neumann entropy given the macroscopic observations. What are the macroscopic observations depends on the system, but for a simple system, it would be energy, angular momentum, charge, things that you can conserve quantities. I'm sorry if those definitely.
Okay, next question. Yeah.
If we assume the eigenstate summarization hypothesis without ergodicity hypothesis, is there any postulate we could be expected? Okay, this question.
I didn't quite hear the question, but I think part of the question is probably whether in some sense a black hole behaves ergodically.
Yes. Is there any postulate about black hole, the seminology, and the seminal hypothesis, some hypotheses we could expect it from the eigenstate summarization?
Yeah. So, well, one of the striking discoveries in the last decade which unfortunately also would have called for a somewhat different lecture than the one I gave, is that the dynamics of an evaporating black hole is highly chaotic. It's believed to have maximal quantum chaos. So it's believed that a black hole saturates all possible inequalities of how chaotic and ergodic a quantum system can be.
Okay, second question.
Oh, hi, Witten. So do you think that nowadays, how can we use the methods and techniques of quantum information to understand the questions like black hole information and microstates, holography, and the emergence of space-time? Thank you.
Well, I mean, the question was, how can we use notions of quantum information theory to describe black holes? Well, at some level, that's an unsolved problem. But the von Neumann entropy, although I didn't define it technically, is a basic concept in quantum information theory. And the statement that the von Neumann entropy is the area of something is an example of a very limited partial answer to your question. So toward the end of my talk, I was explaining, toward the end of my talk, I was explaining a few of the reasons that people in the field tend to think that what you were asking are good questions. But you were asking questions whose answers aren't really known.
Thank you.
Okay, thank you. So let's end the lecture here. We are starting again at 11. Thank you.
是吧？摄像机位的老师，摄像机位的老师过来一下。这边数学院老师提出一点小问题，咱们一块儿沟通一下。谢谢啊。 话怎么说？
哦，太难是吧？
对。
哦，它应该有。
如果没有的话，我再拿一个。
We are going to have the third talk of today. So after talks by mathematicians and physicists, now we have the talk on computer and information science. We have our great speaker, Andy Yao, who I know for a long time. Andy's wife was my wife's classmate, including Andy himself. They all graduated from Taiwan University. So we knew each other a long time ago, even though we may not meet as early as we should, but we did know each other. And we have been communicating for a long time, and of course, I have been extremely impressed by Andy's great works on complexity, computation, and all that, and that's really impressive to me. But it's actually more amazing to me that he was at the beginning working in high energy physics undergraduate in Harvard, and to be able to change the field and become the major leader of the field is rather unusual. I admire his ability to change and become the leader in the field. And he came back to China about 20 years ago. In fact, he asked me whether it's a good time to do it, and I agree that he should come, and I admire his courage to come back in China 20 years ago. Many people talk about coming back to China, but they never really did, except Andy actually sold his house and moved everything back. That needs courage, and I really think this is a great role model for all of us to see his development, and he has accomplished a great deal in this last 20 years in Tsinghua University. And we are continue to see that he is going to lead the Artificial Intelligence Institute in Tsinghua University, and it will become the important center in the future of China. So in any case, today we are happy to see that he's going to give a very interesting talk called Building Up Computer Science by Asking Good Questions. Andy.
Good morning. It's really a great pleasure to be here. I certainly would like to thank Professor Chou, Professor Yao, because that in Mandarin is really Professor Chou, and for establishing this magnificent conference, and I'm really humbled to be able to join the ranks of Adi Shamir and Ed Witten and other award winners. And I certainly like to thank him profusely for building up this really magnificent event. And actually, I have known Xin Tong for a long time. And certainly, I heard of him even earlier. I think it must be 40 or 50 years ago, that even though he's a few years younger than I am, but actually, even when I went to graduate school, he already was a legend among many scholars, especially among the Chinese, because he was at a really exceptionally young age to have solved major problems. And I was really happy when I went to Stanford University and had a chance overlapping of the teaching at Stanford. And so we communicated quite a bit afterwards. And now it's amazing that we're both in China again, and also we're doing with the same goal of trying to promote basic science in China. So in many ways, I think that Shen Tong has been my role model for a long time. And today, I would like to give a talk on building up computer science by asking good questions. And as we all know, that answering questions is a major mode by which that any science would build up its components and deepen its understanding. And today, I would like to give some examples of questions and the process of seeking answers in the context of computer science, because that's the area that I know best. So asking good questions is very essential for science. And by raising novel and interesting questions, one can lead to new theories, conjectures, or shed light on problems which seemingly to be unrelated. So I'm going to choose my examples from areas in cryptography, complexity, and AI. But let me start by stepping back and look at the question of asking questions in science. I think the best way of that I know of classifying questions is the following. There are two types of questions, and now here is a passage from a classic literature. It says that people see things as they are and ask why, but I dream things that never were and say, why not? And this is from Bernard Shaw, who is a great lyricist. And now, even though the context was different, but I think this is a good way of classifying questions. There are those that you see some natural phenomena, like Isaac Newton. I think the legend has it that when he was hit by a falling apple, and he asked why, and that led to the theory of gravitation. And the latter kind of questions could be exemplified by Charles Kao, who won the Nobel Prize in 2009 for fiber communication. And he was a physicist, and by working in fiber optics, he had the idea that why not use it for internet communications, fast speed networks. And I think that roughly these are two major types of questions, and that the examples that I'm going to give will have questions from both types. And now, what are good questions? Well, one way to see it is that good questions often lead to great innovations, and it could have huge impact, and it creates new industries, generate wealth, or it could transform human society and history. And the other character of good question is that it's very imaginative. And I think that when we were children and we were puzzled by things, and at that moment, in our innocent mind, when we find out the answers, it works like magic. And let me give you some example. For example, the question, can we fly, when we look at birds? And it leads to the airplanes. And can sound be recorded and later recovered? And this led to the recorders. And can we beat bacteria and save human lives? And so this led to penicillin. And so I think that when we talk about good questions, and these are some of the really concrete paradigm that we can take lessons from. And so before I talk about the examples from computer science, let me take an example from a much older science, because computer science is really a young science. I have lived through the growth of computer science from the very early times. And so I think that there are even better examples from the science like mathematics and physics. And so let me take one from physics. The example is about Saturn's rings, and it's about a great physicist, James Maxwell, and who invented electromagnetic theory and really much, much more. And as a young man, he actually solved the mystery of the Saturn rings, even though it was a big discovery for most scientists. But I think that many people did not realize that, because it's really overshadowed by his accomplishment in electromagnetic theory. But today, let's look at the Saturn's rings problem. In 1610, Galilei aimed his telescope at Saturn, and the resolution of the telescope became greater. And in 1655, Hertz realized that Saturn actually has a ring system. It's very beautiful, as we can see here. And now, in 1856, the question, what makes Saturn's rings stable, became a very formal question. It was the topic of a prize. It's called the Adams Prize. I think so. This prize is a little bit different from the prize we are receiving today. They really, it's like an exam, and somebody posed a question. And so Maxwell worked very hard on it. I think Maxwell, at the time of 1856, he was only, I think it's 25. And he worked really hard, and he found a solution, and the prize was given to him for his essay on the stability of the motion of Saturn's rings. And he proved mathematically that the force of gravity would break a thin body orbiting Saturn. So it could not be just a solid type of material. And he predicted that the rings were a large number of particles floating around Saturn. And so the mathematics was magnificent, and as we can see from Sir Airy, who commented it was one of the most remarkable applications of mathematics to physics at that time. And finally, in 1980, the photographs from the spaceship Voyager confirmed Maxwell's prediction because it actually got a good, very close look at it. And really, there are just many, many particles. And it actually continued to make news in the science literature as one investigated the more and more the astrophysics. And so now let me come to the main subject, the good questions in computer science. And certainly, I think that but the best example is by Alan Turing, who in 1950, he published the paper, Computing Machinery and Intelligence, in which that he was contemplating that whether computers could simulate human behavior, whether we can be modeled as machines. And he initiated the idea of today called artificial intelligence. And in particular, he was not just philosophically talking about it, but he, as a scientist, he introduced something called the Turing's test. And he suggested that this could be used as a criteria to see whether we have succeeded in building a machine that somewhat simulate human. And so he imagined that there's a human and a machine in separate rooms, A and B, and they had a text-only conversations between them. And now there's an evaluator who observes the communicated messages. And is it possible for this evaluator to differentiate which one is a machine? And so the point is that if you can build a machine so that a human evaluator would have difficulty to distinguish man or machine, then it will pass the Turing's test. And it's a simple question, but it really is very profound. It would take many, many years before we got some really good answers. And so that's actually 1950. It's really before computer science has become a formal discipline. So let me pause the discussion of this question until later. And let's take it from 1950 and look at the in the meanwhile working on less difficult questions. We are really punching cards, and each night would submit the code to the computer room and wait next day for the results to return. And if by some accident you drop your deck of cards on the way to the computer room, then really nothing can save you. And now that works for quite a bit until in the late 1970s or early 1980s. Personal computers were invented, first at Xerox PARC. And also in that place, people started building networks using something called the Ethernet that have high-speed connection between the different personal computers in the lab. And so this really started a new age for computing, because people since that time gradually evolved into a mode that most people would use personal computers, or we call notebooks, and we communicated with each other, and also with the if you need powerful computer, you can also connect it to them. And now, this change in the computing mode has a profound impact on the on computer science. It has added many components to computer science, particularly the area of distributed computing becomes a major academic subfield. And there are many different conferences which even now, today, they are still there, and that they have grown to be major areas in their main right. But this also gets the theorists very interested in, and I think different people invented different theories for it, but basically we want to model the algorithms in a distributed environment, which involves many parties in order to collaborate and do computations. And for example, even in those days, there were far-sighted people who envisioned one day there could be electronic commerce that connect business together and also with the customers. And to do electronic commerce, you have to be able to do encoding, and hence a cryptography for the not for the military but for the everyday life is envisioned. Maybe someday there would be a community of electronic commerce, and they would need something called a public key cryptography, and for example, in order to provide security and also to protect privacy in general. And another aspect is that in the network computation age, the computation by mainframe computers is not the only cause. Actually, a lot of the computations people would need to do would the major cause would be the communication. So communication and computation hence are integrated together. And so we should have a computation model away from the Turing model. It's just a Turing machine, but it's a network of Turing machines or personal computers collaborate together, and we have to model the communication cost into account. And how do we do that? And so there are a lot of interesting new computational theory blossoms, some of them involving, interestingly, quite advanced mathematics. And it turns out notions like algebraic topology or geometry, they turn out to be relevant for network computation. But that's not our main topic today. And today, I would like to focus on cryptography and also communication complexity that reflects the privacy part and the communication cost part. And of course, computer science marches on, and later on, there are quantum computers, ideas, and so on. And so one usually start by asking simple and natural questions. And so this is about cryptography. And in this area, some of my contributions include the Dolev-Yao security model, pseudo-random number generation model, and multi-party secure computation. I think that they each it's motivated by distributed computation in some aspect. But today I will just focus on the multi-party computation, or MPC model. And MPC is a novel cryptography concept. And the question is that in network computation, where many people want to collaborate, sort of contributing their data in order for the computation to finish. Is it possible to get the desired result, but protect the privacy to the extent that is possible? I mean, you cannot protect your privacy 100% if you want to have some influence on the outcome, but you want that to be the only thing that you contribute without contribute even any bit more. The answer is actually surprisingly yes, because usually it's difficult to imagine that. And MPC is a way that enables multiple databases to do joint computations without leaking its own data, or you can say that it's sharing data without seeing the data. And let me just give a special case to illustrate the point. It's called the millionaire's problem. The two millionaires wish to figure out who is the richer one without revealing any other quantitative information. In the end, both millionaires know who is the winner, but not anything else. And mathematically, it has Alice and Bob, the two parties, and one has a private data x, the other is y, and we want to compare. Is the integer x less than y? Is there any method for these two millionaires in a lush place, like we are here sitting side by side and want to start a conversation, and at the end, you want to know the answer whether x is less than y? And now the question is that, can we accomplish it? And well, the number one answer for an educated person in information theory can very easily see this is impossible. So Shannon's theory tells you exactly when there's something revealing any information. And according to Shannon's information theory, this is not possible. But if you really need to do it, is it really possible that, well, you can think outside of the box, and it is indeed possible. And what I did was to show that it actually can be accomplished by something called a gobbled circuit. I'm going to tell you a little bit about how it is done later. And but I just want to mention that much advancement has been made on MPC, and so the theory and the practice remains a pretty active area today. And actually, I think that it's just in the last few years, it becomes that the practical people become much more interested in it because of the development of the applications. And so the application is because it's a very general type of theory, is that any computation, it's possible to do it at some additional cost to solve the same problem. And for example, to query and computation on confidential databases. And it also includes applications in fintech, data trading, and AI drug discovery. And I would elaborate a little bit on the drug discovery example a little bit later on. But now let me look at how it is done in the kind of the oversimplified case. So Alice would give Bob n sealed envelopes, and they would, assuming x and y are small numbers, okay, small integers, and so I would put a 0 in the first x envelope, and put the rest envelopes with the 1. And so Alice would turn her head, and so Bob, in the meantime, picks up envelope number y to see whether it's a 1 in it or it's a 0 in it. and so the content is 1 if and only if x is strictly than y. But of course, I mean, this is it's not a electronic communication setting, and so what one need to do is to use encryption method to encode the 0 and xy, and send the encoded message from Alice to Bob. So to implement it, you would use keys K1, K2 up to Kn. Each envelope we're using a different private key by Bob, and send the message from Alice to Bob, and now through the oblivious transfer, it's possible for Alice to let Bob get one of the key, which take to be ky. Okay, so without revealing y. So the oblivious transfer is a cryptographic protocol that can be done, and I will not go into how it is done. But essentially, this is the way it is done, and in the simpler case. And now I would like to just one word about the drug discovery, that because millionaire's problem is a it's a toy problem, but actually just in the last few years, people start using it for the collaboration between two drug developing say companies to jointly do drug discovery. So for example, if you have a very rare disease and where data is very precious and scarce, and now each company has some private data, and the company can use it to do drug discovery. And however, if you put together the data from both companies, in principle, the machine learning algorithms can help you to design better drugs. And however, because the data is very precious, the companies would like the computation to proceed and share the profit as a result. However, they wouldn't want the data to be available for the other companies. Is it possible to do such a computation to implement the machine learning algorithm? And in principle, it could. And there are people who actually did it. A couple of years ago, I think there was a paper on Science which described how they did it. And now come to the third example, communication complexity. And this is to model what is the communication cost needed in order to compute a distributed the problem. For example, just imagine it's the millionaire problem, X and Y. And the question is, instead of whether it can protect the privacy, you are interested in just wanting the communication to be done as fast as possible, using a minimal number of bits in order to find out the answer for both people. Can it be done in a small number of bits? So more generally, given a function f and with private data x and y, you would like to know the answer z for Alice, and also z prime available to Bob. And the question is that what's the minimal number of bits it's possible? And let's just do the standard complexity in computer science. So any algorithm for computing f will use the cost of this algorithm to be the minimax the result, namely that this is the worst case cost, and df is the minimax communication complexity of the function, which is defined to be the cost of the best algorithm for this perspective. let's get some feeling. Suppose f is the parity function in the sense that it's the total number of ones in x and y, and if the let's see. Sorry, I think I got it wrong. It's the parity function is just the parity of these two numbers. Okay, and so the result is 2 because x and y each one has to send one bit to the other, and actually this can be done. Okay. Now, however, parity is really the exception rather than the rule. And if you look at the equality function, it's x equal to y. It turns out that one can show that the most obvious algorithm, namely just Alice send n bits to Bob and Bob send the answer to Alice n plus 1, it actually is the right answer. But this kind of takes a small proof. And also for the inequality for the millennials problem, this is also true. But in general, it's not so easy if I give you a function f to know what the communication complexity is. And this df is called the deterministic communication complexity. And since 1979, many variants of communication complexity have arisen from different applications. For example, there is the randomized version when you allow randomized algorithms, and there is the quantum communication complexity when you allow quantum computers and the quantum communications. And there is the non-deterministic communication complexity, and also there are the multi-party communication complexity. And there are many applications in communication complexity. And so it's surprisingly, in practice and in theory, it has led to applications in VLSI design, Boolean circuit complexity, data structure, streaming models, and some more elaborate type of complexity question. And this last one is actually a major result. Because I'm going to tell you a little bit about this last application. But a communication complexity provides in addition to providing a way to evaluate the efficiency of distributed computation, it also provides a valuable approach to study computational complexity. And what's the reason? If you look at any kind of computational process, say a Turing machine or Boolean circuit, during the process, it involves plenty of information and plenty of bits to pass around in the computing structure. And thus, somewhere there is some communication problem embedded in computation. And so, for example, if you can prove a lower bound to the communication complexity of the embedded problem, then this gives you a lower bound to the computational problem. And so considering how difficult it is to derive lower bounds to computational problems, communication complexity is one of the very few set of tools that systematically allow you a paradigm for solving lower bound problems. And so let me just describe one example. And the question is, can linear programming solve the traveling salesman's problem? I think for a while, people were not sure and debated about it. And is it possible to do that? And it's certainly, I think by now, most people believe it cannot. But it's difficult to prove one way or the other, even for the restricted type of computation. And actually, communication complexity provides a way to solve a 20-year-old conjecture of Yanakakis, and that's a very deep question, and it uses the non-deterministic communication complexity. So this is a theorem for Rini et al. In 2012, and Yanakakis' conjecture was in 1988. So this is more than 20 years. It proves the extension complexity of the traveling salesman problem polytope is exponential in n, which is the number of cities. So in more detail, that is saying that even you're adding auxiliary variables in the linear program, the traveling salesman problem cannot be formulated as a linear program of size less than exponential. And this is a pretty stunning result. And now let's return to our first example, AI. AI in the 20th century, since Turing's question, and it has up and downs, but you can see that what I just like to show you is the landscape that is generated by this quest, and it really stimulated a lot of development. And in 1956, McCarthy coined the term artificial intelligence, and he advocated using logic and search. And so people were pretty enthusiastic in the beginning, but after 20 more years, the optimism get dampened, and there is a artificial intelligence winter, number one. And in the 1980s, AI has some revival because the Ed Feigenbaum and others have advocated expert systems using the logical rules and to do useful things. And in 1982, there is a very significant event. The Hinton and Rumelhart, they devised something called backward propagation. This is an algorithm that is used for multi-level neural networks. Previously, people were not able to do efficient optimization using neural networks because they didn't really have a good algorithm for doing it. But in 1982, this happened. And now in 1987, another AI winter happens, and expert systems realize have limitations. And 1993 for up to 2011, and their steady progress. And one heartwarming development is 1997, IBM Deep Blue defeated international chess champion. But even at that time, people were saying that surely we cannot beat Go, world champion, at that time. And so the 20th century, to summarize, in the last half century of the 20th century, scientists found AI to be intriguing. As when we were in universities, and we can see that the applicants, they are mostly interested in AI. But even though people try out different approaches, but didn't come close to the expected result, certainly not the Turing test. But one thing that comes up, and I mentioned there is a back propagation for neural network, that it's really turned out to be a hidden bright spot, even though I think that people were sort of given up on it in the 20th century, except for a small group. And so deep learning is an entirely different paradigm from the traditional algorithms that we theorists, the mainstream theorists, used to, because we all are secret believers of mathematics, and we thought that the only way to design respectable algorithms is to think about the problem for many months and preferably years before we found something really deep and beautiful. And then we are sure before we write the first line of code, it's got to be right. And I know exactly the running time. And now, this is entirely different. To us, this looks amateurish. It's saying that let's just do it in a try and error way. We just let the dumb network learn and get adjusted to the environment. And so let's look at an example to recognize handwritten digit. Are there better ways than the respectable way electrical engineering, image processing people used to do? Is to really to think about what features the figure 8 has, maybe 2 circles and so on, that type of thing, and then use that as a basis. But the network learning people have a different idea. They say that just read a large number of positive and negative samples, the parameters in the network, and hope that it will see the light eventually. I think in Chinese, we have a really nice term. It's the Ngo Bao Chau. So after you have seen enough plus or minus examples, and it turns out that this to be later on, that it turned out to be wonderful. It's not just an ad hoc thing. It can solve many problems. And so this happens in the 21st century, and together with all the powerful technology progress, then we can see amazing things. 2012, the AlexNet make advancement, and people then believe that deep learning is the thing. And 2016, AlphaGo defeated world champion AlphaFold, followed by solving protein folding. And I think that even after 2018, I think that most computer scientists still would still think that Turing's test would be difficult to pass. But overnight, I think 2022, overnight, I think that almost everyone starts believing that finally we have conquered Turing's test. And so so the answer to the Turing test after 17 years, that's why I think it is the #1 example for the good question. And so it has a practical implication, and also it has a conceptual component. I think that we theoretical computer scientists, at least most of us, we just have to become AI scientists from now on, because we realize that perhaps it's really true. If we use the old paradigm, we are doomed to restrict ourselves to a small number of questions, and it's difficult to go beyond that. In order to solve the vast majority of everyday problems, we have to learn machine learning, and so I think that means that the answering of Turing's test is not an end. It really is the beginning of a world where we have to think algorithms in a much broader context. And so let me just say that there are plenty of opportunities abound, and just in AI, I think this is I think this is to me, this is the alpha problem for computer science and AI. It's just to continue the quest and to see that whether we can actually achieve general artificial intelligence. And I think each of this area will become a major area in computer science. And so we can ask both questions, formulate fresh models, propose solutions, and demonstrate experience. And I think in the abstract, I promise that I will discuss the art of asking good questions with you. And so I think that asking good questions really is an art. And certainly, if you want to be a good researcher, you have to find your own way of asking good questions that is most suitable for yourself. But let me just offer you my thoughts on it, reflecting my attitude. So how to choose problems wisely? I think the first, it has to be attractive or 漂亮, and it should be simple, it should be novel, it should be surprising. And number two, it has to be important, 要重要的, that there must be people who care what the answer is, certainly at least within your own field. And preferably, it has an appeal, has a universal appeal, that it can appeal, it transcends academic boundaries. And my test is that if I can explain this question and the results to people at least in the more theoretical disciplines, mathematicians or physicists, then I can think it has a universal appeal to you. So with this, I end my talk. Thank you very much.
Well, thank you very much, Andy. It's a very good thing to make us to asking the right questions always. Okay, let's see questions. What is important to questions? Oh, here.
Thank you for your beautiful talk, Professor Yao. Since you talked about a wide perspective of history, I'd like to follow this way to ask a big question. How can we measure the overall impact of the new technology like artificial intelligence in the most important stockholders, including government, researchers, public, and AI industry? Because we think that we might need this new kind of interdisciplinary science today. I know this question is far beyond the purely computer science, but I think that might be a good question. Thank you.
Yeah. So can you say again the main question?
That is, how can we measure the overall impact of the new technology like artificial intelligence, including
how can we
measure the impact?
How can we measure?
Yep.
I think that that for other questions, it may take some argument, but for artificial intelligence, I think that I would bet no one in this audience would question the impact of artificial intelligence, in the sense that if you think about all the different professions, say, if you think people from the government, and if we think about it from the viewpoint of business people, I think that it's obvious that the AI, it already has enabled many businesses to become much more efficient. And for example, that AI not only can replace some of the tedious work, but it can even replace jobs like people who write codes, right? So simple codes right now, AI really can do it. And so I think that in 10 years, I don't think that you can get a job if you kind of work as a elementary coding experts. And so the only question is that how far would it go? But in any case, I think that impact of that kind, we can see it by how the society is already starting to worry about the massive possible unemployment as a result of AI. I think that in 10 years or even earlier than that, most of the factories will be just manned by robots. So for business people, the government people, the impact is definitely there, and it is mostly good, but it also it's something that we have to worry about because it creates problems. And for scientists, I think that I'm not yet worried about my job. I worried a little bit about teaching. I think that I think except for the function that Professor Yao has said, that good professors provide a role model for the students, and perhaps the robots will not. But otherwise, if it's just the knowledge transfer, I think that the AI is going to capable of replacing all of us. And now, I don't worry about my job yet, because I think that we still haven't had a indication that the AI can do really high-level research as we would like to do. But even that, I'm not so sure. Okay.
Okay, so we still have time. Thank you.
Okay.
I just want to give another answer to the question that was just asked. How can we measure if something is really important if governments are worried about it? And I'm serious. They were worried about cryptography and tried to outlaw it and prevent the export of cryptography, etc. Then they got worried about very powerful computers. Then they got worried about quantum computers, and now they put restrictions. And in AI, they try to stop the sale of high-end GPUs to China, for example. That's the test.
Yeah.
Thank you for the talk. And I would like to ask, so right now AI works with deep learning and we have this data training the robots, right? The question I have is there better ways to do it? Or are there ideas of better ways to do it?
Yeah, I think that's the $6 million questions. I think we we all think about it, but my guess is that from now on, AI really is a new science. I think it's no longer a computer science, and the fact is that we have built some really intelligent systems like ChatGPT and so on, and so we can regard it as a new creature. So just think about that on Mars there is some sort of a humanoid which are like the ChatGPT, and they can do a lot of things better than we are. And so the question is that if we go to Mars, and how can we live with those people? And so trying to beat them, I think that one way to do it is that let's think of it as a physics project. You know that on Earth we have these creatures called ChatGPT, right? And now we want to study them, right? I think this is a wonderful thing, in the sense that people talk about neuroscience a lot, and the idea is that we want to look at the brain and so on. I have to say that neuroscience has really good functions because it can try to cure disease and so on. But if we want to understand how brain works, that try to understand how GPT works is a much better proposition, because we can dissect the machine. We can look at as much data as we want, using as much intrusive method as we want. So we are in a much better position of understanding the intelligence of these artificial intelligence systems, and so therefore, one way to do it would be the kind of the old-fashioned way of trying to look at all the data coming off these machines and let's build a mathematical model for it. But my sense is that it will be difficult to do that. I don't believe that there is a neat mathematical theory that we can use to prove how powerful these machines are. Instead, I think that we have to just think, now here is this entity, and if you are a physicist, how are you going to build theory, which may not be the molecular theory, but is sort of a phenomenological theory. But the point is that I think that we have to study it just based upon the principle that can we have a theory that can make predictions. And for example, if I give you a machine and tell you the structure, can you predict it is going to be a very intelligent one or not? I think that's the golden test that one can have in treating it as a science project. So that's my thought.
Thank you.
Other questions? Yeah.
Very nice talk. So my question is on the sense that I would like to hear your thoughts on. There's this article by Wigner that on the unreasonable effectiveness of mathematics in the physical sciences or so. I feel the same way with machine learning or deep learning in general, that we don't really, I mean, it works, we know it's an empirical result, but can you share your thoughts on why it actually works?
I think in very, very restricted cases, there are some progress for very simple networks. But I don't think there is I think that why deep learning works as well as it does is still a mystery. I think I think some physicists think that they see some analogy, with the condensed matter physics and so on. But I'm not sure it's totally convincing. So we don't know, and we may never know. That's my opinion. That it's we sort of that I think that Turing did two great things. The first one is that he, together with other pioneers, they asked the question, what is computation? And they, in a couple of years, they kind of solved the problem, and they think they have known the answer. But in Turing's 1950 paper, he asked another question, which is sort of I think in some way deepened our understanding, because from the original Turing machine, people in complexity theory kind of developed an understanding that the principle that more computation gives you more knowledge. Okay, and the lower level of computers will not be able to fathom the depth of what the bigger Turing machines are thinking. So cannot predict what they are going to do. But usually that's in a mathematical context. There exists something, just diagonal argument, that type of thing. But I think that ChatGPT is a living example to show us how a large number of parameters can do things that we never dreamed about. So I think that the ChatGPT, to me, it gives me a kind of revelation of the original theorems about getting more power for more computation, and I think this is a very rare. So it's something that would be very difficult to quantify, because I think that in complexity theory we have people who kind of argue that it would not be possible to prove lower bounds. So this is I think it's consistent. So therefore that's my basis for saying that one shouldn't try to solve the problem from a standard mathematical approach. And we are very lucky. This is once in a lifetime. This is a century type of opportunity. We happen to run into one systematic method of getting intelligence. And I predict there's another, there wouldn't be another revelation like that for at least 20 years. So I think that everything that we do for the pragmatic people must be coupled with this big model. But of course, you can add other components to make it do a lot of other things, and that's the challenging part.
Okay, there'll be one question from David Castan. Where is he? Okay.
In the critique of judgment, Kant was raising a question, kind of saying that our belief in science is based on the assumption that understanding is possible. It means doesn't matter how complex a system, there should be restricted, not very large number of rules, that using this, based on these rules, we can analyze the nature. And until very recently, we definitely lived in the world of agreement with Kantian expectations. It seems to me that the basic problem which AI arises is whether Kantian expectations are correct. Whether it looks for us now that achievements of AI are not based on construction. Any number of small instructions. For me, the main question is whether it's really we live in a world which disagree with Kantian expectations.
Sorry, can somebody tell me a little bit what's the?
The Kant writes that doesn't matter how complex the system, how complex the system is when we look at it. We'll expect it to be reduced to a number of small rules. Example for him was Newtonian laws. The nature mechanics is very complicated, but it was reduced to a small number of rules. And until now, in all our development, at least of physics, not talking about biology, we lived in this paradigm. We talk about quantum field theory, it's a very complicated system, but it has very bounded number of basic rules from which everybody expected to be deducible. The situation with AI is different. As little as I can follow, it seems to me that achievements of AI are not reducible, at least. We cannot reduce it to number of small rules. That AI wins the chess game, we don't learn anything about how to play chess. It is actually functions in a completely different paradigm, not the paradigm when understanding is possible. When understanding means reduction to a small amount of axioms and rules, but is unbounded, which exactly contradicts the Kantian expectation.
Okay, Yeah, thank you for the question. I think now I understand it. And so it's certainly it's possible that there will not be a simple explanation in the standard sense of postulate and derivation mathematically the power of AI, and mainly because the kind of I think these machines really are just like human intelligence. It's obtained by learning. So these are things that through a very complex circumstances and selection that that human intelligence becomes what it is, and there's no bounded number of axioms from which that this could be derived. And in other words, perhaps the Kolmogorov complexity of the brain is very high. So yeah. So I think I agree with this possibility. In some way I kind of hope this is the case, because it would be a little bit too boring if this time is again we can explain it like the quantum field theory. I think that you will be even nicer if we can build a different basis of understanding, and in some ways it's actually a bit better for us. We have our dignity if it turns out to be the case.
Okay, these are very nice questions and very nice answers, but we should end this lecture today. Thank you very much, Andy.
Thank you very much.
So as you see, at 2 p.m. we have a small gathering for seeing our exhibit of mathematicians, and some of your pictures will be there if you are curious. For those who got awards,